Okay, good. So let's get started. Towards the end of the day, we'll have two shorter talks by Martin and me. So Martin has been a professor at ETH Zurich for around 7 years now, and he has worked on a wide range of topics related to programming languages, including concurrency, dynamic and static program analysis, program synthesis, combinations of programming languages and machine learning, and more recently also probabilistic programming. So go ahead.
Okay. It's on? Okay. Okay, guys. Hi. So our talks are like supposed to be half an hour in theory. In practice, it always runs over. But, huh? It's true. So if it goes over, just stop me, okay? All right. So I want to tell you a little bit about this topic of reliable interpretable AI. Something that we've been looking at in the group for the last few years, and recently a little more. Okay. So I think this is a very important problem. You see in the news all the time various scary articles, right? The dark secret at the heart of AI, and I don't know how well can we get along with machines that are unpredictable and inscrutable. So in the European Union, there is an archive paper which says European Union regulations demand explanation from the models. What are they doing, these black box models? And there was like a recent article also by Hinton on the fact that we need to somehow look at the problem all over again and kind of maybe start all over again, okay? So how many people kind of have an idea what is like interpretable even mean in this space? Like, what's your intuition about this? Any thoughts? Anything? Like, it should be a program that I look at, or like natural language explanation, or like what? Right? So people are trying to figure this out, right? It's not clear, and it's active, and there's a lot of work happening. But one thing I think that kind of going to happen is there's going to be a lot of opportunity for people in this area to contribute to this problem. Really, a lot of the problems are kind of interdisciplinary, and I'll show examples of this. So there's going to be a lot of the kind of advances are going to intersect multiple areas. So machine learning, programming language, probabilistic programming, like Just and Mike talked about, automated reasoning, some of the talks we've heard so far. So somehow we need to combine these things to make steps in solving this problem. All right? So what I want to do is give you a bit of intuition, a technical intuition about some of the work that we've been doing, and one of the latest systems that we've built. We built a bunch of systems with machine learning over the years, but this is like one of the ones that's not yet actually, that's the first time we talk about it. So, if you're in the PODI steering committee, if we submit there, you may desk reject the paper because there is already a leakage of the information, but fortunately, it's submitted elsewhere maybe. So, here's the problem that we're looking at in this space. So this is actually from a paper that's about to appear, or it has appeared already, SOSP. Somebody knows when is it? It should be very soon, but this was an archive for a few months. So this is an example of what happens to neural networks when you show them images, right? And so the question is how good the neural network is. So let's look at the picture. And so what happens here is you have a picture, and the neural network has to decide which way the car should turn, okay? So there is 3 neural networks, each corresponding to the different arrows. So yellow, green, and red. So 2 of the networks say go left, and one says go right on the side. So now on another picture, different picture, this time these 2 networks say go left, and this one says go right. And on the third one, it's right. This is a different combination of networks say different things. Okay, so this is kind of like across multiple networks, they are making mispredictions for different inputs. Right, it's not what you want to go into the building, probably not yet at least. Okay, so there's been a lot of press about this, how to fool machine learning models. Put stickers on the signs, on the stop signs, scratch the signs, introduce perturbations, and so on and so forth. and various researchers in learning and other areas are looking at how to fool the models. So, okay, not surprising, there is work on this. How do you actually find so-called adversarial examples? So these are examples where the network is doing something that's not supposed to be doing, and you're fooling the network. So there's different ways to find this adversarial example. So there's lots of recent work in this space. Okay? So from just techniques like bug finding, if you want to find the adversarial examples, to some actually give you some guarantees about the kind of the network is free of these examples to some degree of confidence. Those typically scale for small networks, okay? Not really large-scale realistic networks that people use. And of course, recently there is, like, as I mentioned, this paper in SOSP by Junfeng's group, collaborators, and some other ones which are more on the systematic testing side. So they try to find interesting violations, if you want, okay? There is related work, and as you can see, it's a very active space of research. So what's the problem we're looking at? So here's the problem we're looking at in this space. We are trying to explain at high level what the network is doing. And so as a sub-procedure, essentially, we need an analyzer that can actually check properties of realistic large-scale networks. So the ones that people actually use in practice, okay? So if you're able to develop such an analyzer, you can use it in various scenarios. So for instance, you can use it to certify cyber-physical systems. So combinations of neural networks and other classifiers, proving robustness of the network, learn actually interpretable specs, what the network is doing, explain what the behavior of the network is, compare different networks formally, and so on and so forth. All right, so this is joint work with Timon, who is there, Matthew Meerman, Dana, Peter Tsankov, and Swarat, so, who is here on sabbatical with us. I don't know where he's sitting. He's there. There he is. Okay. So everybody's here. All right. So here's the problem statement a bit more formally. We can formulate this neural network analysis problem as follows. So we're given a neural network and some model. We're given a property over the inputs. So let's say property over the images that the network takes. And we're given property over the outputs that the network should produce given these inputs. And then we would like to check whether this indeed holds, that for all inputs that satisfy the property on the images, when you run the network, the property holds on the output. Okay? So this is a very hard problem, because this property on the inputs can talk about unbounded or infinite number of image concrete instances, right? And basically what's going on now is that existing solutions, like based on SMT solvers, don't scale to these realistic networks, like convolutional nets, for instance, right? So here's the key observation behind this work. This is, okay, essentially you can think of it as abstract interpretation for artificial intelligence. AI networks are just one example. So here's the key insight that deep neural nets, really what they're performing is really a function, fine transforms on the data, the input, with some restricted nonlinearity, which are the activation functions typically. And then that's on this side. And then on the bottom side here, we have abstract interpretation, the other AI, okay? Where over the years, over the last, so how many, 15, 20, 30 years, there has been substantial advancements in abstract domains, scalable domains, that trade off precision, in other words, approximation with scalability, all right? So this is the insight, to combine these two directions and build a system that can actually check properties over realistic networks and use this procedure for other kind of tasks. So Patrick here is kind of, I don't know if he's happy or not, but he's saying something. So good. So let me give you the idea, like the high-level idea, and then tell you a little bit how it works with some of the abstract domains, okay? So here is on top, what you see is the concrete input. So here's going to be the concrete, just running the network. And here you have some images, for instance, the digit 7, okay? So written in different ways. And now what happens is, let's say we take this digit 7, this image, and you feed it through the network. And when you feed it through the network, it's going to compute different values for the intermediate layers of the network. So if I feed this image here, is going to compute value as 0.01, 0.3, so 0.01 for the first neuron, 0.03 for the second neuron in this layer, and so on and so forth, going through the network. If I fit this last image, it's going to compute some other values for the neurons as I go through the network. Okay? Does this make sense? All right, this should be just how the neural networks operate at a high level. So what is the idea? What is the central idea? Well, the idea is the following. You keep, what you basically do is instead of propagating a single concrete image through the network, you propagate a symbolic image through the network. So rather than running this one and this one separately, okay, we actually propagate a single one, this symbolic image over here, which is described in some way. And what this symbolic image captures is essentially, if you like to think about it more concrete, take a concrete image and make, say, unbounded number of perturbations to this, some set of perturbations, which generates an infinite or unbounded set of images, and then represent this as a formula over here. Okay, so what you can do now is rather than propagating a single concrete image, you propagate a symbolic image, an abstract image for the network that represents a large number of concrete ones, and you propagate this through the network. And when you get to the end of the network, you can check the property that you want. Okay? This is the high-level intuition of the idea. All right? So this is what's going to happen. So I'm just going to tell you like how it happens for particular abstract domains. If you have any questions, just ask here. It's a good time. Right? So one of the challenges here is how to define the appropriate abstract transformer so that it's sound when you move through the network, and to find domains, numerical domains that are actually suitable for this problem. Not all domains are really suitable for this problem. So let me show the example for the zonotop domain. Okay, how many people have heard about this domain somewhere? Of course, Gagandeep and Katerina, right? And okay, so some people have. So this zonotop abstract numerical domain was developed, I believe, by Eric Gubau and Sylvia, I'm going to butcher the last name now. Huh? Puthal, yes. So this is a paper, I think, from early 2000s, right? And so that's existing work, okay? We're not developing a new domain here. We're taking an existing domain that's already been developed. And what happens in this domain, though, we're going to kind of adapt it and apply it to this setting. So let's think of it, what happens here. You can think of it the following way. An abstract neuron now, rather than a concrete neuron, which takes a value, you have an abstract neuron. And this abstract neuron actually is represented by the following affine form. So we have a concrete tree of valued coefficient here, and a summation over some error terms and coefficients over here in front of the error terms. These error terms here, okay, they range between -1 and 1, and these blue terms here, they kind of capture the magnitude of the noise of the error, okay? So an abstract neuron, in some sense, kind of represents a lot of different concrete neurons. And here we have another abstract neuron, so different abstract neuron. Now you may ask yourself, I'm going to have two abstract neurons, like what's their concretization, which is standard in analysis, something you need to define. And the concretization for this domain is basically a polytope centered around these coefficients over here. So if you pick concrete values for these blue variables, you would get some shape like this, okay? So centered around over here. So this is the zonotop abstract domain, and that's one of the domains that we use in this setup. Okay. So abstract neurons captures a set of possible concrete values for these neurons. Combinations of abstract neurons lead to different shapes and different sets of concrete neurons, each of which are inside this blue box. One thing to say about this domain, which it's fast, but the problem is that in some cases, and it's actually not closed under joints and meets, okay? So many of the numerical domains are actually closed under meets. What is this thing? This should be a meet here. This is wrong, so meet, okay? Cap. All right, so you can lose information in two places. One is here in the join, and one is here when you have a meet, so two places. Let's look at it a little bit more. So we're given the input image, some image that you are given. And then what you do is you introduce perturbations to this image in some way that you think it's interesting to you. So you could introduce, for instance, shading or lightning perturbation or darkening perturbation. So whatever you think you want to prove the image with respect to. You can do rotations and other kinds of perturbations, right? So here, for instance, in this example, we have 784 pixels, and these are the pixels here. And so, for instance, we can say for pixel 0 stays at 0, pixel 1 here has some constant plus some variability here, the range for that concrete pixel. Now it becomes a range, okay? Because this E1 here ranges between -1 and 1, all right? So this is the start of the analysis, right? It generates a huge set of images. And what you may want to check now is this huge set of images that sits here actually satisfies actually produces the same classification. So they classify it in the same way. All of them, get classified to 7. Good.
How to decide which noise to put in the input?
How to decide which noise to put in the input? I mean, we play with different kinds of noise settings, but this is something that's domain specific. You have to decide. It's a good question, like what kind of maybe rotation shifts and these kind of things that you want to do. One thing I want you to pay attention is that this verification problem is not for, in a sense, saying for all the images in the world. Okay, this is really a verification problem for this network and perturbations to this image. Okay, so these two. All right, still unbounded or infinite number of images. So once you propagate this constraint for the network using the standard transformers of the particular numerical domain like zonotopes, you are going to get at the end some constraint. Okay. And that constraint, it may look like this. So x0 to x9, this might be the 9 abstract neurons, and each of them ranges over some symbolic formulas whose concretization is many, many possible values, concrete values of the neurons. All right? One thing we do to kind of get a bit more precision is we don't always join, but we have a power set domain and partially join sometimes, and we keep sometimes a set of zonotopes around, just to get a little bit more precision. But more or less, you get like these formulas here. Once you get this formula here, your job is to check whether the label that you want, 7 in this case, is actually the one that is produced for all of these concrete images that are represented by this whole formula here. So the standard way that you can do that is to say, well, I want, all of the what is the J? Yeah, all of the labels here. Okay, so I want the one that is produced to be greater than them. So this is the target label here, so 7. Okay, and so this value has to be greater than any other label that can possibly happen. So if it's 7 greater than 0, then 1, then 2, then 3, and so on. Of course, if you meet this with the constraint over here, and this is non-bottom, then the condition is violated. If it is bottom, then you have proven that all of the images that are over here actually represented here in the concrete actually are classified as 7 in this case. Let me give you like one slide on just how a little bit more technically how it works. So this is just a structure of a tiny neural network. So don't worry if you kind of don't know what ReLU is. So you have 4 nodes here, so 4 neurons. And these neurons are firing and they're like fully connected. So let's look at this one over here. And this neuron is separated into 2 parts, the computation. The first part is computing the affine computation. So what this does is it takes the values of the previous neurons here and then does the affine computation, so combines the values with the weights. And then once it's done this, it applies the nonlinear activation function in order to compute new values. And that's how it progresses for the network. And then that value gets propagated down to other neurons. Okay. So what is this nonlinear activation function? So there's different ones: sigmoids, tanh functions, ReLU activation functions, different ones. Okay. So ReLU is one of these functions that's like widely used. So this is the graphical representation of this function. So basically, the derivative of this function is 1 when the slope, right? When the value is greater than 0 and 0 otherwise. And the reason why you may want to use this function over some other ones is some of the other ones that you may have seen that go like this. Basically, the slope gets very, very small in new training and the convergence gets very slow. So you have to kind of define the abstract transformer for this particular ReLU function, activation function, which is down here. I'll not bother you with the details. This is fairly standard use of the numerical domain underlying operators like the mit here and the join. Okay? So the basic idea, right? You have these artificial intelligence algorithms, decision trees, graphical models, neural nets, so on. And you want to analyze them with a large-scale methods that scale to large-scale analysis like abstract interpretation, numerical approximations. So we built that system. It's called AI2. So this is a system that will get released soon, hopefully. Basically, the system supports different kinds of neural network, fully connected, convolutional, the kind of max pooling, flattening functions, and the main activation function that's used now, which is the ReLU. So this covers most of the practical neural networks that people write today. The supported domains are interval, zonotope, polyhedra, bounded power set domain, right? Mostly the one that you want to use is zonotopes and not polyhedra, which is extremely expensive. And the gain in precision is only marginal here. Okay? So here's some preliminary results. How you, to compare the effectiveness of this system that we built. So basically, this is the MNIST. This is the character data set where you characterize digits, handwritten digits from 0 to 9. And this is the name of the neural network and how big it is. So this one has 6 layers and 15,000 neurons. So these are way beyond these existing works like SMT-based works. Just don't scale to these sizes. This one is almost 60,000 neurons. So most realistic networks seem to be in the range of 50,000 to 150,000. So this starts getting into this space, okay, the more realistic ones. On the x-axis here, what you see is the specification. So what it means is that basically how much you can actually relax, right? So how much can you actually, so over here, the closer it is, it means I allow more perturbations. And the less it goes, it means there are less and less perturbations allowed. And so this green one is the interval. It's a really simple domain. And basically, when the specification is more complex, it fails to prove anything as robust, right? It's 0 here. And as it gets like, I allow very, very little perturbation, it says, oh, now I'm very good. Okay, I can prove everything. So it's kind of like this. The zonotop domain seems to strike like a good balance. So over here, about 75% of the images where this specification was active will actually manage to get proven by the zonotop domain. And the red one is the bounded relaxation where we don't keep a single zonotop, but we keep 4 of them at a time. And similar results we can see for the larger convolutional network. This is CFAR10. This is an image data set, okay? So once the system gets released, I guess you'll be able to plug in your own images and actually draw and introduce perturbations like he asked and see what happens. Okay, so this is a little bit what I wanted to tell you about some of the work we've been doing. I think it's a very interesting space, and I think people in the room are uniquely kind of positioned to get into it. There's many interesting problems here. A lot of problems here in the system I told you. For instance, the current implementation of zonotop can be made a lot better. The abstractions can be scaled more specifically for these domains and really scaled to the largest possible networks. Looking at other kinds of networks, not convolutional ones, like recurrent networks, residual networks, different kinds of networks, what robustness even means there, dealing with noise in the input so that there's a probabilistic noise introduced. It's just an open space, and it's a very, very interesting space. So that's it from me. Thank you for the attention.
Thank you. Okay, questions? Yeah.
So for the example that you gave, you said that you work on a fixed input image that you characterize the robustness against a particular permutation or particular somehow kind of noise. So what would it take to scale this work to actually work against arbitrary inputs for a particular class of perturbations?
arbitrary inputs, meaning that you basically have a quantifier outside, like for all images.
Yes.
That are, yeah, this is, so I guess the question is, do you even want to do this? Because one thing you can do, of course, now is enumerate them, but this is not great. I mean, right now, in a sense, it is doing for all, because the concretization of this represents a very large set of images.
But you start from a single.
You start from a single and then you
image.
draw it, but this symbolic thing already represents, it's basically saying for all images in this symbolic thing, this holds.
Yeah, but
Yeah.
it could be that I have some other image where I do small perturbation in the network falls
Yes.
apart.
I mean, right now we'll just like enumerate, like we'll take the image, perturb it. I don't think that it's possible that having common perturbation to a large set of images, whether that makes sense even, because they're completely different. So if you're perturbing, I don't know, you remove the S from the stop sign versus, I don't know, scratching the dog, okay? These are not the same kind of perturbation. So I'm not sure the problem statement even is good there.
But you could do like a small, like Gaussian blur or something like that, and that probably.
That may work. Yeah, that's interesting. That's interesting. So this is, I'm telling you, like the limit right now with this method. This is like I think the most scalable right now. The limit is this, barely getting to the realistic networks. So inserting even more symbolicness initially, who knows what happens? We'll see. Yeah.
Okay. Yeah, Mike.
Could you go to the results slide for a second? I just wanted.
Result slide, 1 second.
Yeah, there we go. So what is the interpretation of the y-axis here?
The interpretation of the y-axis is that 100% is like the total number of images in the testing data set. And then the interpretation is that for how many images you actually manage to prove the spec. So here, if it's like, it says this kind of weak spec, which, I mean, good spec, it's like quite relaxed. You manage to prove it for 75% of the images. And for the intervals, for that spec, you didn't manage to prove it for any image.
So perhaps at least for CFAR, so is it the case that all of these images can be demonstrated to be robust, or all these networks and imaging?
So this is not, this is trained, we analyze the CFAR trained network,
Sure.
but here is for a small number of images.
But you've selected some set of
we
images
just
that
picked
you
some,
know.
Yes.
Okay,
That's not tricky set, just pick some set.
Yeah, exactly.
And that's it.
That's what I wanted to clarify.
Yeah,
But so, and then for cases where verification does not go through,
Yeah.
can you generate counterexamples for those? I mean, those should, in some sense, be adversarial examples.
The problem is, due to the approximation, like the mids and the joints are approximate.
Yeah.
So a counterexample doesn't mean that the image is not robust in the range.
Yeah, that's fair.
It just means that
Yeah.
God knows. Maybe it's robust, maybe not. And
Okay.
so you can apply, so we start looking at like the standard abstraction refinement. You
Yeah.
try to see if it's a concrete example.
Yep, yep,
It
yep.
has not been explored much. Yeah,
Okay.
yeah,
Have you-
that's a good point.
For some of those rejected images, have you actually seen, so have you done any exploration of trying to generate counterexamples, and how do they compare to other techniques and how they've generated
Yeah,
adversarial
I mean,
examples?
you can see some counterexamples. So I think that there is a nice problem that probably hasn't been looked at much, so which is generating meaningful counterexamples,
Yeah, of course. Yeah.
not those with the scratches.
Yeah, that's what I was wondering. Do you have any
Yes,
perspective
we have
on
not
how?
yet. We're looking at
Okay.
this.
Okay, all right.
Yep.
Sounds good.
Okay, maybe one more question? No? Okay, but then thank you.